can see your screen. You have 8 minutes, Mohammed. Thank you.
Okay, thanks. So good afternoon, everyone. I will try to summarize some of the work that our lab have done in collaboration with different partners over the last few years in this work, and then to give some lessons learned, let's say, through case studies. So let me mute some of the audio first. So yeah, from the left to right, I would try to explain the teleoperation architecture that we use to teleoperate different robots that have different kinematic structures, from the smaller ICAD to its larger sibling in the right, the ICAD 3, to Ergo Cub, through to the newly developed Honda robot avatar. In fact, we started very early with the basic premise of trying to command two functionalities, basically locomotion and manipulation, so grasping. This is the basic interaction with the environment. Then we included more sensing modalities, and we changed our hardware. We evolved our hardware to a slightly bigger robot with more sensors. And then more recently, here on the bottom left, we have the Ergo Cub, which is even taller, lighter, and more aesthetically pleasing, let's say. And as you can see, more and more we are moving away further and increasing the distance. For instance, on the top left, you can see that we were teleoperating a robot that was in the same place as the operator. On the top right, you can see that the robot actually was visiting the Biennale Museum in Venice, 300 kilometers away from the operator who was in Genoa. And this instance on the top left, on the bottom left, is the operator in Genoa, and the robot actually in Bologna. And finally, the robot is actually not even developed by IIT, but a robot developed in Tokyo, in Japan, and was teleoperated using the same inverse kinematic algorithms from Genoa. So the story of this architecture started in 2018, and as I said, there were two modalities that we were interested in commanding: locomotion, and we used at the time it was popular, the omnidirectional treadmills, and a commercially available headset. We developed some software wrappers around it to interact with our middleware, which is Yaro, and we were able to command ICAP to walk, to grasp objects of various sizes. The robot was equipped with two stereo cameras in the instance. Recently, the architecture evolved even more. It became more complex, maybe, but more comprehensive and also more flexible, in the sense that there are a large software stack on the operator side and a large software stack on the robot side. Not everything is necessary. You can swap pieces. For instance, in the manipulation, you have different modalities and functionalities. On the locomotion, you can command locomotion using a treadmill, using a joystick, using what we call the iFeel shoes, which are shoes that are equipped with sensing modality for force torque, so impact forces on the ground reaction forces. You can command walking in that way. We added the possibility to command facial expressions to allow smoother interaction with humans also. And then on the feedback side, we had more and more complexity. So we got rid of the joybags and we incorporated various different types of gloves, with some of which are with haptic feedback as well. And some robots that we have built and interoperated have some what we call skin sensors, which are basically capacitive sensors that allows you to feel the touch in specific parts of the robot body. The cool thing about this architecture is that you can run, as you see, given an established IP route or a VPN. In fact, you can run the operator side on a very remote place compared to the robot side. Also, all of these smaller pieces of code can run on different laptops depending on their availability. For instance, most of the code that is responsible for the measurements of the robot quantities or commanding of the robot whole body controller, we prefer to run it on the robot torso. So there is a CPU inside the robot also. But apart from this, we are not restricted, so we can run also the software that grabs the commands coming from the operator inside the robot or inside a PC that is on a third different place. It depends on the setting and requirement. This work was recently published in the Sense Robotics, if you are interested. For what concerns the operator side, we have worked on developing some sensors, sensorized suit. This is the iFeel suit, we call it. It has some IMU sensors that you wear, and they allow you, as you can see in the video, to measure human kinematic and dynamic quantities, but also to make predictions of the human and kinematic and dynamic quantities. And there is two different versions of the suit. For what concerns the shoes, we have a shoe that started with an actual force-torque sensor. Then we moved to this malleable material, which is basically composed of a network of capacitive sensors that allows us also to detect ground reaction forces. These kind of sensors allows us to, as you can see, measure the human motion, but also to predict it. In this video, you can see there is a slide prediction with the human representation in red in 1 second ahead in time because of how we construct the dynamic index kinematics are doing that. For what concerns the robot side, I don't know if you can see. Sorry. Yes. For what concerns the robots, we have currently these 3 robot avatars. We call them robot avatars. The left one is the iCub3. It's equipped with FT sensors, with artificial skin, with stereo cameras. It's 1.25 meters tall. It's 50 kilograms heavy, with 54 degrees of freedom. And recently we enlarged it a bit with a 1.5 meter tall ErgoCam model that is almost the same weight, and with some real sense cameras and better wrist mechanism and grasping mechanism. For what concerns the Honda robot, in fact, it's developed by Honda, of course, but what I can comment about it is that it has a sophisticated hand with fingertip FT sensors. So it allows precise grasp, impulse manipulation, and these kind of things. We use this architecture that I described earlier, for instance, to visit the ICRA 2023. So students and PhD students in our lab were roaming the hall in London from Genoa and interacting with different robots in the exhibition floor through the ErgoCam robot. So here, the Boston Dynamic dog robot here is commanded by an operator in place, but our robot was teleoperated from Genoa and is able to take the hat from the dog, pass it to the other hand, pass it to a different robot that is a unitary robot, and it was fun. There was some, of course, latency issue that arise from the large bandwidth requirement by the real sense camera and the internet channel that was available in the exhibition floor. To solve this, we worked on compression techniques. So we used the FFmpeg compression to reduce the requirements on the visual feedback. Still, there is some possibilities of improvement in this case because you can actually have a better sense of depth rather than just a projection on the headset. We use the same architecture but with a modification. Sorry for the noise. To command the
Mohammed, you have 30 seconds left.
Sorry?
If you could wrap up, 30 more seconds, please.
Yes, sorry. It's the last slide. So just to emphasize the flexibility of this architecture, this robot runs on ROS, not YARP. So we needed just to plug a middle software piece of code that translates commands between our software and the robot side. We can move the inverse kinematics from Genoa to Tokyo, and we can run it on either side. It will give the same result. Okay, take home messages. So being flexible is king. As I said, you should be able to insert new interfaces easily. Uh, Communication latency is key. One thing to work around it is to use compression techniques for messages. You can restructure the way you communicate with the robot, and then for lack of depth sensation through visual feedback, you can render on spheres rather than just projections, or you can use fisheye cameras. For what concerns future work, we are working on studying more social aspects of this kind of scenarios. So body ownership, when does the operator feel that he is actually transported? What is the interaction partner perception of this robot identity? Yeah. If you want to see more, you can check this barcode on the page. Thank you.
Thank you, Mohammed. We have time maybe for one quick question. I was going to ask you to give a quick lessons learned, but you put that on your last slide, so I will skip my question. Any questions from the remote audience? No? Well, thank you, Mohammed.